So an extension of the friction is kind of where we're going with this particular section. Rolling friction is the next one that we're going to talk about. It's exactly what it sounds like, right? If your car had zero friction, the tires would just spin and you would just sit still, right? It would not move. And so some friction always exists between the wheel and the road. You need it to exist. If you've ever hit black ice or if you've ever hit water on the road and realized you didn't have friction, it's not a fun feeling, right? And so you're always going to have friction. In fact, the video that we watched showed those tires and that tread and why that tread's so important to funnel the water away so that your tire's touching the road. And so rolling resistance then is the first definition we're going to get to. It's the cumulative effect of all resistive forces that reduce the freedom of motion of a rolling object. So yes, rolling objects are much easier to move. If you've moved furniture and put it on some type of furniture dolly, it's amazing the weight that you can transport when it's on wheels, right? If your car breaks down, you get a couple guys behind you, put it in neutral, they can push the entire car. They probably couldn't pick it up, right? And so even though we think of wheels as just freely rolling, there's friction involved. It has to be, or they would not move. And so rolling resistance is often called rolling friction, and you're going to see that notation with the big F and the RF. That's the rolling friction. Propelling force then. So you have kind of the sum of the forces is what we've been thinking. Well, now we have like a propelling force, which is basically adding the applied force and the rolling friction. What you'll notice about the diagram down here is the applied force is going one direction, the rolling friction is going the other direction. So it's working against the applied force. That's what the friction is working against. So as the tire is trying to move, the friction is actually pushing the opposite direction. And of course, you don't want more friction than you're applying, or again, we're going to have balanced forces. But that's what your propelling force is, and that's how it's moving the vehicle. So we have an example here. A 125 kilogram soapbox derby car rolls down an inclined plane that makes an angle of 10 degrees. If the magnitude of the rolling friction is 20 newtons, what is the car's acceleration? So we're going to look at all the things that are happening to this car. The first thing we're going to look at is that we have this plane. Once again, just like when we did a box sitting on an incline, we're going to, if we were to draw this right triangle out, we would have the cosine giving me the parallel movement, the sine giving me the perpendicular force. Or backwards than that, sorry. The sine giving me the parallel, the cosine giving me the perpendicular one. And so we're going to use that same concept. We're going to say there's a force that is pushing it down. That's called gravity. And so to calculate that force, we're going to take the 125 kilograms. We're going to multiply that by our gravity, right? And you can use a negative here if you have it drawn that this way is negative, you could say negative there because we're talking about acceleration. All right. And that is being multiplied by the sine. Remember that parallel now when we draw that right triangle is going to be the sine of that degree that they've given us, which is 10 degrees. That's one of the forces working on it. All right. One of the forces working on it is rolling down a hill. That's gravity. Gravity's working on it. But remember, if we were to draw gravity straight down, we have this right triangle that comes, right? Just like we did on an incline. That's 10 degrees. We're trying to find this guy. We're going to use sine there. All right, the other force then acting on it. Prior to this, we said it was a frictionless table or whatever, right? Now we're talking about a rolling friction on it. And they've actually told us the rolling friction. We don't have to calculate this. The rolling friction that they gave us is 20. It is working against that force that I just calculated down here. Because it's working against it, we are going to subtract that force that's working against it. So that is what we would think of as the sum of the forces. All right, that's the sum of the forces. The gravity, because it's just rolling, and then the friction, the rolling friction there. Then remember, the sum of the forces, we've said it about 100 times, is mass times acceleration, right? It gave us its mass, 125. Acceleration is what we're solving for. So go ahead and solve for that. What is my acceleration for this car? I'm going to correct this because when I set this up, so this is a good little lesson here. I set this up and I'm saying the rolling friction is working against it. So that means that even though in our brains we normally say gravity pulls it down, if I did the working friction is working against it, I have to use that one as positive. Does that make sense? So if I use my friction as negative, then I have to use my gravity as positive. So only one of those can be negative. 54, it was 3 significant digits. So you should get 1.54 meters per second squared. That is my acceleration given the mass that I have and the rolling friction on that vehicle. Right. So analyzing these inclined planes, assign a coordinate system. So for this example, if they have my XY, what they're trying to do is they're going to draw this incline, then they're going to assign what I mean by X and Y. For the very reason that we get the question, why are we using sign for X at this point? Well, that's because of the way that we drew this, right? Again, if negative makes more sense to go down for gravity, and this is your negative, then when you do gravity, you're going to do negative, right? And that's going to be positive. And then you need to think about what this angle has created. So this 28-degree angle actually created this other triangle that's right here, and that's what they've pulled out here so that you can see where your sine and cosine come from. All right, so assign the coordinate system, draw your diagram, resolve the vectors. So resolve means break it up into XY components. That's what we did when we multiplied by the sine or when we multiplied by the cosine. We're breaking it up, resolving it. Way back from when we did vectors, that's what we did over and over. When the airplane was moving, we broke it up into X and to Y movement. Develop the equations, determine the type of friction involved, and then solve the problem. So here we have steel blocks. The first block is 2.5 kilograms. The second one's 15 kilograms. They rest on the surfaces. They give us the incline of 38 degrees. The blocks are connected by an ideal string passing over an ideal pulley. For this system, they've given us this first guy. What does this first guy mean? What does that mean when they give me mu of S? So mu of S is my static coefficient. Mu of K then is my kinetic coefficient. So this is the one we're going to have to use to figure out if it's moving. This is the one we're going to have to use to figure out how fast it's moving. All right. The blocks are initially held at rest. Determine whether the blocks will move when released. That's an important statement. They're actually telling you they're not putting any initial velocity on it. They're not pushing it. They're just letting go of it. All right. Calculate the acceleration if it moves. All right. So let's look at this right here. A couple things when we're drawing this. We have two blocks. We have one that is just sitting there. All right. We have one that is inclined. This guy's going to have to be broken up. We're going to have to break this vector up into components. This we won't have to. He's not at an incline. All right. And so we have two different things we have to think about when we're doing this one. Then once we've established kind of what those are, we're going to do some calculations. I personally, when I draw my free body diagrams, I actually write on it what the mass is of each individual one. Just so when I'm doing it, I can see which one. So like if I were drawing this, I would actually write the 15 here and I would write the 2.5 there. That's just my personal method because when I have so many things going on, I come back to looking at my picture, all right? So for this one, we have to calculate a few things. We need to first figure out what the normal force is on this incline block. The normal force on the incline is going to be the guy that's going up. This is we're going to use the cosine, just like we've been doing. So we're going to say that 15 times the 9.81 times the sine then of 38, sorry, not sine, cosine. I'm doing backwards. Cosine of 38 degrees, we're doing normal first, not x, is going to be, and round it, we're going to round to 1 decimal place for right now. I think at the end, we're going to put it less than that, but we'll just do it a little bit more as we go through the process. So this is my normal force, and I'm going to label it as such. That's my normal force. Sometimes you'll see it as the force of gravity in the y direction, all right? Meaning perpendicular to my surface, all right? We're going to do the same exact thing to figure out the force of gravity going with the incline. So the force of gravity going with the incline, you'll sometimes see it like that. And so we're going to then do the same exact thing, but we're going to do the sine here. Yeah, I jumped ahead and did that one first. All right. And again, I'm taking it out a few decimal places till the end, just to be a little more accurate, right? So I have those two pieces, all right? Now what I need to do is I need to figure out the friction working against the block that's on the hill. Why the block on the hill? Well, the block on the table is not going to move given any other circumstances. Objects in motion stay in motion, right? Objects at rest stay at rest. So if he wasn't tied to the other block and we just let go of him, he wouldn't go running down the table and then slide down the hill. That's not what he's going to do, right? And so I'm going to have to compare the friction of the entire system to the actual thing that could potentially pull it down the table. And that's the guy on the incline, right? Does that make sense? And so I'm going to first calculate the friction of the two blocks, the static friction. So remember, my static friction coefficient that they gave me was the 0.61. So they gave me this, and they gave me 0.61. So remember, to figure out the force of friction, we're just going to multiply that guy times normal force, all right? So we have a normal force of this one. Normal force of this one is literally just its weight, just a positive version of its weight, right? So again, depending on how you decide, if I decided that this is negative, then that means this guy is going to be pulling one direction and the other one's going to be pulling the other direction, all right? We're just trying to figure out which is bigger. So I'm going to take that. I'm going to do this one first because he's pretty simple, and I'm going to say 0.61 times 2.5 times 9.81. Again, you could use negative here if you wanted to because that's going to force it the other direction. But in this case, if you use negative for the static friction, it's to the right, okay? So we'll look at the positive and negative at the very end. So if I just calculate that, I get that his static friction looks like that. That's the force of the static friction on the first block. I'm going to do the same thing to the second block, but now I'm going to use normal. His normal force is what we multiply by. He had to be broken up into components. I'm not just going to use his mass times his gravity. That's not what I'm going to use for him. I'm going to use that normal force, this force that I calculated right here. So I'm going to plug in the 115.9. The perpendicular force to the incline is what's going to be used here for his friction force. So we're going to say 115.9 here. His static friction looks like that. Those are the two pieces of friction that are acting on this. So we have to add them up. That's the total friction acting on this block. So if I were to take this and say, okay, I want this direction to be positive, then that means my gravity pull is negative, right? But when you're comparing which one's bigger, you're really looking at absolute value. Think of it like when you're adding numbers. If you add two numbers with opposite signs, which side of the number line will you end up on? Well, the one that's further away from 0, right? And so when I compare these, I'm going to compare the 90.59 to the 85.5. Which one's bigger? Well, this guy is. He's bigger, which means it's going to go down the hill. Yes, it's going to move. So yes, this is going to move. It will move because this force that's pulling down right here is stronger than the static force on the entire system. So yes, we did a negative movement here, but when I'm comparing greater than, less than, you want to think absolute value because it's which one's pulling harder in their direction, whichever their direction is. All right? Questions on that one? We have the acceleration of it going down the hill, right? And we have the friction, now kinetic, working against it, okay? And so we're going to do the same thing we just did with the static, but we are now going to do with the kinetic, and we're going to subtract because it's working against our gravity, all right? And so I'm going to scoot this up a little bit so you can still see it. So we're now going to take our kinetic coefficient, which was the 0.50, all right? We're going to take our gravity, and I'm going to leave gravity just at positive right now. I'm going to leave it right here so we can see an overall acceleration. At the end, we can decide that it's going down the hill, and we'll say that it's moving negative. But just for the point of calculation, because we are getting the difference between the two, all right, we're going to say then we're going to subtract. What are we going to subtract? Well, we're going to subtract the 0.5 times the 2.5 times the 9.81. And we are also working against the 0.5 times that 115.9, the normal force on that one. So we've got our force of gravity working against kinetic friction. That's why we're subtracting those two pieces. All right? Now all of that equals our total mass. What's the total mass of the system? Well, it's the two blocks added together, the 15 and the 2.5. That's going to equal mass times acceleration. That's what we're solving for. So we take this whole left side, we do our number crunching of that guy, and we divide by the 17.5. What do you get? And we are taking squared. So 1.16 meters per second squared. If you decide that down the hill is negative, you could put a negative in front of your meters per second squared. That's perfectly fine. But the reason we subtracted is that friction's always working against you. So if my gravity is pulling me this way, friction's pulling me that way. So we're subtracting because they're working against each other. Had it been someone pushing it, we would have had gravity and them pushing it down the hill, and that would have been a plus. That would have been adding those. A skier and her equipment have a total mass of 63 kilograms. She skis down a straight slope that makes a 6-degree angle with the horizontal. Her initial velocity is 1 meter per second down the 800-meter long slope, and she reaches the bottom 47.5 seconds later. What's her average acceleration? Use Newton's laws to find the net horizontal and vertical forces. Then use the equation which is your kinetic friction, to find your kinetic friction going down is what they're trying to find. All right, so average acceleration. This is way back in our brains, okay? This is from the very beginning where we found acceleration in all of our acceleration formulas. So our acceleration formula, one of our acceleration formulas is that you can find your acceleration if you take your change in x plus your initial velocity multiplied by your change in time over your time squared. Oh my goodness, way back when. So, change in x, well, how long is the slope? Well, they told me the slope was 800 meters long. Initial velocity, they told me that too. They said her initial velocity is 1.00 meters per second. Change in time, well, they told me it took her 47.5 seconds to go down that hill over my change in time squared. That is going to be her acceleration. That's how fast she's going. I'm going to take it out a little bit further just to make sure that we get very accurate, but significant digit I think should be one more over. So 2 significant digits, but right now I'm going to leave it this far for right now. When I calculate it, to answer the question, like to box it in, we're going to take it to the 2 significant digits and we're going to say 0.67, or you can underline that it's going to be right there. All right. But that would be my acceleration, 0.67, and I'm going to go ahead and write my units for my acceleration, meters per second squared. The other piece of it is they want us to break it down into components, okay? So they want they want that normal force, they want that x force that's going down the hill. So we're going to do the same thing we've been doing. We're going to take her mass times gravity times the cosine to figure out that vertical, and the mass times the gravity times the sine to figure out that horizontal, right? And then we're going to calculate kind of that mu that they want us to get to. So we're going to break it down first just like this. We have the force of gravity in the y direction. That's this way, right? So we're going to use cosine, just the same reason that we've always been. Right? Because when we draw that angle out, it's going to end up being the adjacent side. It's a very tiny hill, so it's 6 degrees. All right. If we do the y, should get something like that. Again, I'm going to hold off on the significant digits for just a little bit. And then we're going to break it down to the x. Same thing we've been doing this whole time. In this last quiz that we did, we talked about we're trying to find our coefficient of friction, right? We're trying to find that mu. We know that our frictional force is going to be mu times our normal force. So that much we know. The sum of the forces acting on this, well, the sum of the forces acting on this would be, we're going to do it this way. Whatever is happening with gravity. So we have gravity. I'm going to push him over here a little bit. The force of gravity, and we're going to say in the x direction, plus the friction force is the sum of the forces. And that is going to equal our mass times our acceleration. Our mass times our acceleration. All right. So if we want to figure out what's happening with the mass and acceleration, we're actually going to try to find this guy because we just found him. We know all the pieces. All right. So I'm going to switch it around so that mu is all by itself. I'm going to say my mass times my acceleration minus my force of gravity in the x position. And then I'm going to divide by my normal force, which is technically my gravity in the y position. And that is going to be my coefficient that I'm looking for. All right, so all I've done is just done a literal equation and solve for the variable that I need, right? So we're going to plug all that in. Her total mass, well, they gave that to us. Her total mass is 63. Acceleration we solved for. We're going to go ahead and use the big long decimal there. Minus the force of gravity in the x position. That's what we already solved for. This is why I went ahead and broke it down. Divided by the normal force, also known as the force of gravity in the y direction. And divided by that. All right, so now we're solving for that coefficient. You did it 100 times on review sheets and quizzes, but now we have a little pieces that we have to kind of put together and figure out, right? All right. Before that, they kind of gave us some information and we just did a straight division. Now we're going to say, okay, we have to take our mass times our acceleration. We have to subtract that gravity pull down the slope, and then we have to divide by that perpendicular pull, which is your normal force. Yeah, the 2 makes a difference. You should have gotten probably half of that if you didn't multiply by 2. So go ahead and calculate the coefficient of friction. Coefficient of friction on that slope, by the way, should be rather tiny. You should have gotten something like that. It is slippery, to say the least. Should have done 2 times 50 minus 2.5 times 8 over 8 squared.